In this video, we'll be looking at Chapter 1, Section D.1 on unions and intersections. Let's take a look at a blank Venn diagram that has two overlapping sets, set A and set B. Now if I take a thick pencil and I shade in all the elements of A, and then I shade in all the elements of B, what I've done is I've shaded all the elements of A or B. So let me redraw the outline of the circle here. And what I've said is that any element, whether it's in set A alone, set B alone, or in set A and set B at the same time, doesn't matter, as long as it's in one of those areas, that element counts. We define this as the union of sets A and B. And we have a special notation for this. It kind of looks like a U. We say A union with set B. And this is our notation for the union. So what this notation right here is saying is I can take any element that's either in A, B, or both at the same time, and it doesn't matter which. Now let's take a look at another Venn diagram, another blank Venn diagram that has, again, sets A and sets B, and they're overlapping. So this time I'm going to take my thicker pen and I'm only going to fill in the area where they overlap. Now the elements that belong in this section right here have to be in both A and B at the same time. So if we write that out in words, I'm looking at the elements that are in both A and B, and we call this the intersection. And that makes sense, right? These words make sense. It's where the two circles intersect. And again, we have special notation for this. The intersection of A with B. And look at this symbol here. It looks like an upside down U. It's the opposite of the union. Instead, it's the intersection. Now, both of these Venn diagrams are examples of non-disjoint sets. And what that means is these two sets overlap. Right? There is a section there where they intersect. And so let's take a look at an example of disjoint sets. Okay, so in this empty Venn diagram, we have two sets, set A and set B. But notice in this case there's no intersection, there's no overlapping. And so these are examples of a disjoint or of disjoint sets. Okay, disjoint means that there's no intersection. And so in this case, if we try to find the intersection of set A with set B, we see that it doesn't exist. There's no overlapping, so this produces an empty set, which is written with the symbol here. We can still do the union of A and B, and any element that's in either A or B would count. So a union for disjoint sets is still possible, but an intersection of disjoint sets is not possible. So let's take a look at an example problem. Here we have two sets, set A and set B, and they're populated with some numbers, and we see that they're intersecting. So these are non-disjoint sets, and we have a universal set here, which is essentially the integers from 1 to 10. We're asked to find two things. We're asked to find the intersection of A and B, and we're asked to find the union of A and B. So in this case, it might be helpful first to actually list the elements or members of set A. So that's the first thing I'm going to do. And remember, set A is defined as anything inside this circle. So I have 2, 3, 4, and 7. Okay, likewise, set B is going to equal 1, 3, 7, 8, and 10. Okay, and then the numbers 5, 6, and 9 are in neither of the sets. So remember, for the first question, we're trying to find the intersection. Okay, so the intersection of A and B is the area where the two overlap. And so I can quickly see that from the Venn diagram. And we see that the only numbers, or the only elements that are in that overlapping section are 3 and 7. And we can also see that 3 and 7 occur in both sets. Now the union of A and B is simply any number that falls within the two circles. Any number that falls inside both circles. So that's all of these numbers in here. Okay, so that's 1, 2, 3, 4, 7, 8, and 10. And notice the integers that are not included in this list are 5, 6, and 9 because they're outside the two circles. Alright, let's take a look at one more example problem. Here we're not given the actual Venn diagram, but we are given the number set. So we're given our universal set, which is all positive integers less than or equal to 12. Set A is all the prime numbers less than or equal to 12. And set B is all the factors of 12. And we're asked to find three things. We're asked to find the complement of set A, the intersection of sets A and B, and the union of sets A and B. So again, it might actually be helpful here to list the sets. So the universal set is going to be all the positive integers less than or equal to 12, which is essentially 1, 2, 3, 4, 5, 6, and all the way up to 12. The prime numbers less than or equal to 12 are going to be 2, 3, 5, 7, and 11. Remember that 1 is not a prime number. And the factors of 12 are 1, 2, 3, 4, 6, and 12. Now I could draw a Venn diagram to help me find all of these different sets and the unions and the intersections, but I actually don't even really need to do that. We can draw a Venn diagram at the end to check our work. But first let's start with the complement of A. Remember, this is all numbers within the universal set that are not part of A, right? So if I have A here and the universal set here, what I'm going to do is just cross out all the numbers that appear in A from the universal set, like so. And any number that is left over is going to be an element of the complement of A. So the numbers that are left over are 1, 4, 6, 8, 9, 10, and 12. So there's the complement of A. Notice that some of these numbers show up in set B, but that's okay. Alright, the second set is the intersection of sets A and B. So these are all the elements that are in common with both sets A and B. So I'm going to go ahead and circle those in red here. So all the numbers that appear in both A and B, well, I have 2, I have 3, and that's it. So the only two numbers that are in the intersection of A and B are 2 and 3. And finally, I'm asked to find the union of A and B, and these are all numbers that are in either A or B. So I'm going to underline in blue all the numbers that should be appearing in the union here. And 2 and 3 repeat, so I'm not going to write them twice, but I have 1, 2, 3, 4, 5, 6, 7, 11, and 12. And just for quick verification of that work, here's the Venn diagram that goes along with these sets, and you can inspect it to make sure that what I've done up here is correct.